We are going to start the first chapter for your mathematics for economics, which is sets. So, although some of you might have mathematics in 11th and 12th, but some of you might be very new to maths. So, sets is a really easy chapter, and I hope this video will help you in ways which you won't even imagine if you're new to maths. So, without a further ado, let's get started. So first of all, let us talk about what basically set is. So a set is a collection of well-defined, distinct objects thought of as a whole. Here, you need to emphasize on two words, well-defined and distinct. The objects in a set should be well-defined and they should be distinct. Distinct means that there should be no common elements, but they should be different. Every object's membership in the set must be clearly decidable. If you look at this Venn diagram right here, so here I can create a set called as A. And I can place my element inside the curly braces. Now we denote a set by using capital letters A, B, C, D, etc. You place your elements inside the curly braces and you call these small letters as elements or members of a set. Let us see the solved example right here. Write the set of vowels in an English alphabet. So we know that the vowels are A, E, I, O, U, right? These are the only 5 alphabets that can be counted as vowels. Therefore, this is a set. Is it well defined? Of course it is. Are there distinct objects? Yes, all of them are distinct. So, in order to be classified as set, a set should be well defined. Also, it should have distinct objects. So, given any object, we must be able to definitely decide if it belongs to the collection. This is the well-defined rule. For example, I'm talking about rivers of India, and here I talk about the river Ganges, let us say. So, will it belong to this set, the set of rivers of India? Of course it would, because it is a part of rivers of India. But if I take it to be river Nile, for example, would it belong to the set rivers of India? Of course not, because it could be a part of the set rivers of the world, but not of India. So River Nile is not included in the set rivers of India. Alright? So, beautiful girls in a class. Now, beauty is subjective, okay? It varies from person to person. Everybody has a different perspective of beauty, right? So, is it well defined? Obviously, it is not, because if I'm going to ask a person to make a set of all the beautiful girls in a class, their set could be different from some other person. So it is not well defined. So I cannot clearly state if it is a set or not. Only well defined collections are treated as sets in mathematics. So here, clever students, they are not well defined. So if you see this practice question right here, state whether the set of good cricket players in India is well defined. The set of good cricket players in India, right? Obviously, it varies by opinion. It is subjective again. So obviously it is not a set. All right, let's move ahead. Now, a set can be represented in two standard ways. First is the roster or the tabular form, and second is the set builder or the rule form. If you see the roster form right here, it lists all the elements which are separated by commas inside braces without repeating any. So you can see they have listed all the elements using commas, right? If you see the set builder form, basically it states the common property, right? For example, A is equal to X such that X is P, or X such that X is P, like this, right? So you can, these colons right here, if you see them, they basically refer to such that. So when you're reading it, you may use such that instead of colons, right? A such that X, A is equal to X such that X is a digit, right? Now, what is the descriptive phrase method? So basically in this, you describe the rule in words instead of symbols. So if I give you an example for it, if you see this, okay, this is in the roster form. sorry, this is in the set builder form. Okay, and you need to convert it into the roster form. Roster form means that you have to convert it into the tabulation method, right? If now what are they saying? Let us see this. Okay, so they're saying x such that x is an odd number. So first we got to know, okay, x is an odd number, and second condition they have given to us is that it lies between 1 and 9, including 1 and 9, right? 1 and 9, both of them are odd numbers as well. So we can create a set using one capital letter, and then we start by 1, 3, 5, 7, 9. So we have converted a set builder form into a tabulation method or the roster form, right? So that's how we do it. Let us solve this question as well, that write the set B in set builder form. Now we have to convert it into set builder form. How can we do it? Let us use the same method. Okay, I'm taking B as the set. B is equal to x such that x is an even number. Okay, and x lies between 2 to 10. Okay, so this is going to be the answer for this question right here. So you can, if you have been given roster form and you have been asked to convert it into the set builder form, or vice versa, you may do it like this. Now here we come to the types of sets. Okay, first is the empty null set. So empty null set is also known as the void set or the zero set as well. So a set containing no element is called the empty set, void set, denoted by the symbol phi. Alright, so if you see in this Venn diagram here, we have no elements in this Venn diagram. Okay, so we basically denote this set with the help of phi. This is known as phi, and you can also denote it by just writing that A is equal to an empty braces. It would mean the same thing, okay? For example, the set of Indians who have walked on the moon is a null set. Obviously, there are no Indians who have walked on the moon, so therefore it is an empty set. All right, so the empty set is a subset of every set. So this is the universal property of an empty set, that it is a subset of every other set. For example, I take a set. Okay, let us take a set to be A. Okay, so phi would be the subset of A. We are going to learn more about subsets, but for right now, just remember that an empty set is a subset for all the sets. Okay, now let us move ahead to this example right here. Is A is equal to x such that x square plus 9 is equal to 0? X is real a null set. So if you see this equation right here, x square plus 9 is equal to 0. First, let us solve this equation. Okay, so from here we get x square is equal to minus 9. Obviously this is not possible, right? If I'm going to solve it further, it is going to give me a complex or an imaginary number. So x should be real. Obviously the answer would be a null set, so I can write it as A is equal to empty braces. All right, now you may try this question. It is again similar. What we have been given here is x square is equal to 4. So when you solve it, okay, you get x is equal to plus minus 2. Now plus minus 2, these numbers, they are not odd in any way. So again, you will get a null set or a void set. Okay, so let us move forward. Now the other type of set is singleton set. Okay, a set containing exactly one element is called a unit set or a singleton set. If you see right here in this Venn diagram, there is only one element in the set A. Okay, so that is why it is known as a unit set or a singleton set. So if you see the general form right here, A is equal to A. Okay, here we have only one member or element inside the set, and that is why we refer it to be a singleton set. For example, present Prime Minister of India. So when you're going to write it in the roster form, you are going to get Mr. Narendra Modi, which is just one, which is a singleton set and a unit set as well, right? Now, you should be, very vigilant in also knowing the fact that if you take this to be a set, okay, if you're given this, Do you think it is a zero set or a singleton set? What do you think? Of course, this is a singleton set because it contains one element inside which is known as 0. So wherever you have been given this set or this representation, always consider it to be a unit set or a singleton set. Okay, it is not the null set. A singleton set always exactly one element. It always has exactly one element. That means that n of a is always equal to 1. What is n of a? So number of elements in set A. Okay, it is always 1 in case of singleton set. Now let us see the example here. It says, what is the minimum possible marks obtained in a test as a singleton set? Okay, so we have to write the set basically. Now the minimum possible marks in a set could be 0. Okay, considering that we have no negative mark. Okay, so we can write it to be like this. So it is an example of a singleton set or a unit set. Now we are talking about finite set. So a set is finite if it contains a countable limited number of elements. The listing process comes to an end. So for example, let us create a set. Okay, so A is equal to 0, 1, 2, 3, 4, 5. Okay, count how many elements here. There are 6 elements here. Okay, so obviously this set is countable. That means I can count it. So that is why I'll call it a finite set. Fine. Now, students in a class, we can count students in a class, therefore it is a finite set. Digits 0 to 9, we have almost 10 elements, right? We can again count them. Coins in a purse, so they are countable. A finite set can always be written in the roster form. We can write it in the roster form like this, right? Empty set. The empty set is also considered a finite set with 0 elements. We consider the empty set, okay, which is 5 or which we denote by this to be a finite set, okay? Now, every subset of a finite set is itself finite. What do I mean by this is that if I'm going to consider making some subsets from it. Subsets means that I am taking some elements and creating more sets from this set, okay, from my principal set. So B is equal to 0, 1. I have created one more set, and C is equal to, maybe I can create it to be 4, okay. Now, if you see set B and C, which are the subsets of set A, right? So you may see here that they both are finite. That means they're countable. N of B here is 2 and N of C here is 1. Okay, so both of them are finite. So every subset of a finite set is itself finite. Okay, if you see the solved example right here, right? Now we have been given, is C a finite set? Okay, and what is the condition given to us? That X such that X lies between 0 and 9. Let us create a set C. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, how many elements are there in the set C? It has 10 elements and therefore it is a finite set. All right, let's move forward. A set is infinite if the number of its elements is unlimited. That means the counting process never ends. Okay, so the set of natural numbers, if I say that create a set for the natural numbers, so how are you going to do it? You're going to be making it like this. 1, 2, it starts from 1, right? So 1, 2, 3, 4, 5, and so on. You're going to use these ellipsis dots to show continuity, because obviously I cannot write all the natural numbers in my roster method in the form of tabulation. I cannot do that, right? So the set of natural numbers, the set of points on a line. Infinite sets usually cannot be written in roster form. Therefore, they are defined by intention. You can use the set builder method. Okay, also you can, basically depict them this way. A subset of an infinite set may itself be finite or infinite. In the case of finite sets, when we talked about that a subset of finite set is always finite. But in case of infinite set, a subset could be infinite as well as finite. Okay, ellipsis dots are used to indicate the pattern continues without end. We use the ellipsis dots, right? So here, show that A x such that x is a natural number. So obviously it is going to be an infinite set. You can denote it this way. Okay. Now, is the set of points on a line segment finite or infinite? Explain. Obviously, the set of points on a line segment are infinite. Okay, so it is also going to be an infinite set. All right, let's move forward. Now we come to equal sets. So two sets A and B are equal or identical if they contain exactly the same distinct elements regardless of order. So here order does not matter. What matters is that both the sets A and B, if we take, let us take an example that we have two sets A and B, okay? They should have the same distinct elements. Order does not matter. So if you see here, this example, 1, 2, 3 and 3, 1, 2. They have the same distinct elements 1, 2 and 3. Order does not matter. So therefore, they would be classified as equal sets. We denote equal sets to be A is equal to B. Okay. They overlap. So that is why we have depicted them to be equal. So they are overlapping. All right. Formal condition. A is equal to B if A is a subset of B and B is a subset of A. That is, every element of each is in the other. Okay, so this is the condition. Now, if you see the solved example right here, it says that A is equal to 1, 2, 3, 4 and B is equal to 2, 3, 4, 1. Again, we have the same distinct elements 1, 2, 3 and 4. That is why both of these sets A and B are equal. If you see this practice question, A is equal to price, quantity, income and B is equal to income, price, quantity. Again, we have the same distinct elements, right? Therefore, these are equal sets. So here basically it should have the same distinct elements. Order does not matter. Now let us talk about equivalent sets. So two sets are equivalent if there is a one-to-one correspondence between their elements. They have the same number of elements. So here elements to be same is not necessary, but what is necessary is that the number of elements should be the same, right? They are denoted by A is equivalent to B or A is equivalent to B. So you can always denote it by these two signs. Same count, different content. So equivalent sets have equal cardinality. Okay, they share the same number of elements, but need not share elements. Okay, so the number is same, but the elements are not same. Every pair of equal sets is equivalent, but equivalent sets need not be equal. So every pair of equal sets is equivalent, but equivalent sets are not equal. You have to remember this. These are very important, concepts. So if you see here, A is equal to PLAN and B is equal to 1, 2, 3, 4. Both of the sets A and B, they have 4 distinct elements. Okay, that means the cardinality of A is equal to the cardinality of B, which is equal to 4. Therefore, they would be classified as equivalent sets and we are going to represent them like this. Alright. Are the sets formed from the digits 1 to 5 and the letters of the word house equivalent? So, let us do this question together. Alright. So, we would be considering, we would be two sets. A is equal to 1, 2, 3, 4, 5. Okay, and B would be the letters of the word house. HOUSE. Both of them have 5 distinct elements. Therefore, both of the sets are equivalent. Alright. Now, the universal set omega, okay, so this letter is basically known as omega, is the totality of all the elements under consideration in a discussion from which all the other sets are drawn. So if you see this part, this entire region, okay, is basically your universal set. Okay, and all the sets are basically derived from the universal set only. All sets discussed A, B, C are formed from elements of omega. The universal set changes with the context of discussion, so it does not remain the same always. It varies from question to question, right? If I say for sets of positive even integers, now here I am denoting my two conditions, that it should be positive and second that they should be even. So here the totality of all the elements would be 2, 4, 6, 8 and so on, right? So let us see an example, that A is equal to all male students in Rajasthan and B is equal to all female students in Rajasthan. What is a suitable universal set? So the totality of all the female students and all the male students gives us all students in Rajasthan. So this is going to be your universal set. If A is equal to set of all rivers in India, what would be a suitable universal set? It would be all rivers in the world. All right. Now we come to our next concept, which is a subset. Okay. A set B is a subset of A if every element of B is also an element of A. Written, B is a subset of A. So as you can see here, all the elements inside the set B are part of the elements of set A as well, right? That means we can say that B is a subset of A. This is how we denote a subset. Okay. So B is a subset of A means that B is a subset of A. So this basically denotes this. Every set is a subset of itself. You have to remember this reflexive rule, that if you look at this Venn diagram, A is a subset of A. Okay, B is a subset of B. So every subset is a subset of itself. The empty set is a subset of every set. We have already studied this when we were studying the empty and the void set, right? So phi is a subset of A here and phi is also a subset of B here. Okay, a subset cannot have more elements than its parent or superset. Okay, let me explain this to you as well. So if I take A to be, let us say n of A, the number of elements in A is 10. And the number of elements in B, I take it to be 5. So the number of elements in B should be always less than or equal to number of elements in A. Okay, that means that when B is a subset of A, it should always have elements which are less than or equal to set A. Okay. Now let us see the solved example. If A is equal to Roma, Nita, Neelam, Nalini, Leela and B is equal to Roma and Leela, show that B is a subset of A. Can you see that every element of B, Roma and Leela, they are present in our set A, Roma and Leela. So here we can therefore say that each element of B belongs to A. Therefore, B is a subset of A. If you see here, if A is equal to 1, 2, 3, 4, 5 and B is equal to 2, 4, 6, is B a subset of A? Of course. Do you think it is? No. Because here, as you can see, we have 6, right? Which is not present in A. Therefore, B is not a subset of A. Okay, let us move forward. Okay, now let us talk about what a proper subset is. So B is a proper subset of A if every element of B belongs to A, but A has at least one element not in B. That is, A is not equals to B. Okay, so we denote it by B is a proper subset of A, or to be like this. Okay, difference from subset. So basically this allows B is equal to A, but this requires B is not equals to A. So B could be a subset of A even if B is equal to A. That means that they are overlapping. Okay, that means that they are equal, right? But if you want to be a proper subset, it would require that A is not equals to B, like this. Okay, because although B is a part of A here, that every element of B also belongs to A, but there would be some elements in A which would not belong to B. Okay, So phi is a proper subset of every non-empty set. We have already seen this. Phi cannot be a proper subset of itself. A cannot be a proper subset of phi unless A is equal to phi. Okay. Okay, let me explain it to you through this example. If you see here, A is equal to 1, 2, 3, 4, 5 and B is equal to 1, 2, 3. Now, although every element of B belongs to every element of A, but there are also some elements in A which do not belong to B, like 4 and 5. And that is the condition for proper subsets, that A should not be equal to B, that all the distinct elements should not be equal. Therefore, B is a proper subset of A. Okay, similarly, if you can see here, they are asking you, is B a proper subset of A? Now, can you see here that the distinct elements of A, B and C are same as the distinct elements of B, which are A, B and C? Therefore, these sets are equal. But for a set to be a proper subset of some other set, what is the condition? That it should be that both of the sets should not be equal. Therefore, here it is just a subset and not a proper subset. Okay. Now the power set of a set A, written P of A, is the set of all possible subsets of A, including phi and A itself. So when we are talking about subsets, so first we have seen that phi is a subset of every set. And we have also seen that the reflexive property, which says that a set is a subset of itself. Okay. So if I take any set, okay, let us take A is equal to 1 and 2. Now I have to create subsets for it. So first subset is going to be phi, because we have learned that phi is a subset of every other set. Then I can construct 1, then 2, and then 1 and 2. 1 and 2 is the set itself. We have also seen in the reflexive property that A is a subset of itself. Okay, a subset is a subset of itself. That is why. So we can easily know how many subsets could be made from a set using this formula right here, 2n. Okay. So if there is a set which has n elements, okay, so P of A, that is the power set. Power set comprises of all the sets, all the subsets of a set. Okay, it has 2n elements, that is subsets. P of A always contains phi and A as members. So if you can see here, we have a set A. Okay, and what is n of A? That means how many number of elements are there? 1. So what are going to be the subsets for the set? We would have two subsets. Okay, here we have again a set A comma B. How many elements are there in the set? 2. So if I plug it in, 2 raised to the power n, I'm going to get 4. Here we have 3 elements, right? 3 elements. So 2 raised to the power 3, which is 8. Now here we have been given this example, find P of A if A is equal to ABC. So here again we have created a power set of A, which is phi A, B, C, AB, okay, BC, AC and ABC. So we have a total of 8 subsets. Okay, I've already done this example. Okay, let us move forward. Now, disjoint sets. So two sets are disjoint if they have no element in common. That is, their intersection is the empty set. So basically, what do I mean by intersection? Is that A intersection B is equal to phi. This is basically the symbol of intersection. Intersection means that how are they basically overlapping, but here we can see that they are not overlapping anywhere. These are completely disjoint. They have no common region, and therefore I can say that A intersection B is phi, right? Phi means that they're not overlapping. So they do not have any elements in common. Okay. A is equal to 1, 2, 3 and B is equal to 4, 5, 6. They share no elements. That is, they are disjoint. Okay, they have completely different elements. They do not have nothing in common. Okay, that is why. If you see this practice question, are the set of odd numbers and the set of even numbers disjoint? So if I construct a set of odd numbers, so it is going to be 1, 3, 5, 7, 9, and so on, right? And if I construct a set of even numbers, so it is going to be 2, 4, 6, 8, 10, and so on. So are they again overlapping somewhere? Do they have the same elements? No, they won't. So these sets would be disjoint sets. Okay, now let us talk about the cardinality of a set. So the cardinality or the cardinal number of a finite set is the number of distinct elements it contains written as n of a, right? So let us start with the cardinality. It basically tells you how many members are there in a set. How many elements are there in a set, right? So an empty set would always have 0 elements. Fine. Here, this is the union rule, okay? Which basically states that n of A union B is equal to n of A plus n of B minus n of A intersection B. So if you can see right here in this Venn diagram, okay, this region is n of A intersection B, okay? So what basically they're saying is, when I'm saying n of A union B, I mean this entire region, okay? This entire region is my A union B. Okay. Now, when I'm saying n of A, I basically mean this region. Okay. When I'm saying n of B, I basically mean this region. Okay. So I am adding n of A plus n of B. And what I'm subtracting is n of A intersection B, this area. Because obviously when I've added n of A and n of B, this region was counted twice. So I'm subtracting it once from my rule. Cardinality helps solving counting problems involving overlapping groups, surveys, class data, etc. Now let us solve this example. Okay. In a class of 25 students, so that means the union set is 25. 12 take economics. Now let us consider A to be economics. Okay. And here B to be politics. Okay. Now, in a class of 25 students, 12 take economics and 8 take economics but not politics. That means that 12 take economics. That means n of A is 12. Okay, this entire region from here is 12. Fine. And they say that 8 take economics but not politics. That means this area. Okay, this area is 8. Now they are asking find the number who take both. So to find the number who take both, I need to find this area basically, right? Because this is intersection of economics and politics. So how will I find it? My entire A was 12, okay, minus this was 8. So 12 minus 8 gives me 4, which is this area, right? So therefore, there are 4 students who will take both economics and politics. Let us do one more practice question. Okay. So in a class of 50 students, 30 take economics. So this is the class of 50 students right here. Okay. Now I'm going to write it here that n of A is 30. 30 takes economics. N of B is 25. That means 25 takes mathematics. And 10 take both. Which basically means this area. Right? So n of A intersection B is equal to 10. How many take economics or mathematics? Which means we need to find n of A union B. Let's plug in the formula. N of A union B is equal to n of A which is 30, plus n of B, which is 25, minus n of A intersection B, which is 10. What do we get? 55 minus 10, that is 45. That means that there are 45 students who either take economics or mathematics. Fine. So we will be learning about Venn diagrams in our next class. So till then, take care and bye.